Good day, I am Trixie Q de Los Reyes of BS Ed Math 3201, and now we are going to tackle about proving in abstract algebra. Let's proceed to the exercise number 1. For each group in the following list, find the order of the group and the order of each element in the group. What relation do you see between the orders of the element of the group and the order of the group? And here's our given. Z sub 12, U of 10, U of 12, U of 20, and D sub 4. Let's proceed to the another page. Consider C sub 12 by the definition, the number of element of a group, infinite or infinite, is called its order. G is used to denote the order of G. Since C sub 12 is have the element of 0 up to 11, the number of elements is 12, or simply saying Z sub 12 is equals to 12. Now let's proceed to the next page. Now we will find the order of each element. Mod 12 is equals to 3, and so on and so forth. Therefore, the element under 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 0. Therefore, the order of 1 is equals to 12. For the number 2, the elements under 2 is 2, 4, 6, 8, 10, and 0. Therefore, the order of 2 is equals to 6. For number 3, the elements under number 3 is 3, 6, 9, and 0. Therefore, the order of number 3 is equals to 4. For number 4, the elements under number 4 is 4, 8, and 0. Therefore, the order of number 4 is equals to 3. For number 5, the element under number 5 is 5, 10, 3, 8, 1, 6, 11, 4, 9, 7, 2, and 0. Therefore, the order of number 5 is equals to 12. For number 6, the elements under number 6 is 6 and 0. Therefore, the order of number 6 is equals to 2. For number 7, the elements under number 7 is 7, 2, 9, 4, 11, 6, 1, 8, 3, 10, 5, 0. Therefore, the order number 7 is equals to 12. For number 8, the elements under number 8 is 8, 4, and 0. Therefore, the order of number 8 is equals to 3. For number 9, the elements under number 9 is 9, 6, 3, 0. Therefore, the order of number 9 is equals to 4. For number 10, the elements under number 10 is 10, 8, 6, 4, 2, 0. Therefore, the order number 10 is equals to 6. For number 11, the elements under number 11 is 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1, and 0. Therefore, the order number 11 is equals to 12. Let's proceed to another page. U of 10. The element of U of 10 is equals to 1, 3, 7, and 9. Therefore, the order of U of 10 is equals to 4. By the definition, the number of elements of a group is called its order. For now, let's proceed to the order of each element. For number 1, the elements under number 1 is 0. Therefore, the order of number 1 is equals to 1. For number 3, the elements under number 3 is 3, 9, 7, and 1. Therefore, the order of number 3 is equals to 4. For number 7, the elements under number 7 is 7, 9, 3, 1. Therefore, the order of number 7 is equals to 4. For number 9, the elements under number 9 is 9 and 1. Therefore, the order of number 9 is equals to 2. Let's proceed to another page. U of 12. The elements of U of 12 is equals to 1, 5, 7, and 11. Therefore, the order of U at 12 is equals to 4. By the definition, the number of elements of a group is called its order. And now we are going to proceed to the order of each element. For number 1, the elements under number 1, mode 12, is equals to 1. Therefore, the order of number 1 mod 12 is equals to 1. For number 5, the elements under number 5 mode 12 is 5 and 1. Therefore, the order of number 5 mode 12 is equals to 2. For number 7, the elements under number 7 mode 12 is 7 and 1. Therefore, the order of number 7 mode 12 is equals to 2. For number 11, the elements under number 11 mode 12 is 11 and 1. Therefore, the order of number 11 mode 12 is equals to 2. For the fourth one, U of 20. The elements under U of 20 is 1, 3, 7, 9, 11, 13, 17, and 19. Therefore, the order number 20 is equals to 8. By the definition, the number of elements of a group is called its order. Now, we will proceed to the order of each element. For number 1, the elements under number 1 mod 20 is 0. Therefore, the order of number 1 is mod 20 is equals to 1. For number 3, the elements under number 3 mod 20 is 3, 9, 7, and 1. Therefore, the order of number 3 mod 20 is equals to 12. For number 7, the elements under number 7 mode 20 is equals to 7, 9, 3, 1. Therefore, the order of number 7 mode 20 is equals to 4. For number 9, the elements under number 9 mode 20 is 9 and 1. Therefore, the order of number 9 mode 20 is equals to 2. For number 11, the elements under number 11 mode 20 is 6 and 0. Therefore, the order number 11 mode 20 is equals to 2. For number 13, the elements under number 13 mode 20 is 7, 2, 9, 4, 11, 6, 1, 8, 3, 10, 5, and 0. Therefore, the order of number 13 mode 20 is equals to 12. For number 17, the elements under number 17 mode 20 is equals to 4. For number 19, the elements under number 19 mode 20 is 10, 8, 6, 4, 2, and 0. Therefore, the order of number 19 mode 20 is equals to 6. Now, let's proceed to another page. D sub 4. the element of D sub 4 is equals to R sub 0, R sub 90, R sub 180, R sub 270, horizontal, vertical, diagonal 1, and diagonal 2. Therefore, the order of number D sub 4 is equals to 8. By the definition, the number of elements of a group is called its order. Now, let's proceed to the order of each element. For R sub 0, the elements under R sub 0 is R sub 0. Therefore, the order of R sub 0 is equals to 1. For R sub 90, the elements under R sub 90 is R sub 90, R sub 180, R sub 270, and R sub 0. Therefore, the order of R sub 90 is equals to 4. For R sub 180, the elements under R sub 180 is R sub 180 and R sub 0. Therefore, the order of R sub 180 is equals to 2. For R sub 270, the elements under R sub 270 is R270, R sub 180, R sub 90, R sub 0. Therefore, the order of number R sub 270 is equals to 4. For horizontal, the elements under horizontal is horizontal and R sub 0. Therefore, the order of horizontal is equals to 2. For vertical, the elements under vertical is vertical and R sub 0. Therefore, the order of vertical is equals to 2. For diagonal 1, the elements under diagonal 1 is diagonal 1 and R sub 0. Therefore, the order of diagonal 1 is equals to 2. For diagonal 2, the elements under diagonal 2 is diagonal 2 and R sub 0. Therefore, the order of diagonal 2 is equals to 2. And this is the end of exercise number 1. Before we proceed to exercise number 2, let me show you the Cayley table of D sub 4. Wherein the identity of D sub 4 is R sub 0. Now, we are going to our next page, which is the exercise number 2. Let Q be the group of rational numbers under addition and let Q be the group of non-zero rational numbers under multiplication. In Q, list the elements in 1/2. In Q, list the element in 1/2. Q under addition, 1/2 is equals to n times 1/2 element of integers equals -3 over 1/2, -1, -1 over halves, 0, 1/2, 1, and 3/2, so on and so forth. For Q star, 1/2 is equals to 1/2 raised to n times n elements of integers equals 1/4 over 1/2, 1, 2, 4, 8, so on and so forth, in which the final answer is 2 raised to n times n elements of integers. Now, let's go to the next page, which is the exercise number 3. Now, let Q and Q star be as in exercise 2. Find the order of each elements in Q and Q star. Q under addition, let A be the element of Q, In case number 1, if A is equal to 0, then every positive integers n satisfies NA equals 0, hence the order of A is infinite. In case number 2, if A is not equal to 0 and A is equals to P over Q, where P, Q, an element of integers, and A is not equals to 0, the NA equals 0 implies P equals 0. Thus, Q equals 0, which contradicts the assumption that Q is not equals to 0. Therefore, no non-zero rational numbers has infinite order in Q. Hence, the only element Q with the finite order, the identity element 0, and absolute 0 equals 0 raised to 1 equals 0, absolute 0 equals to 1. Now, let's proceed to the another page, which is Q star times X. Suppose that Q star is a set of non-zero rational numbers under multiplication. The identity is 1 raised to 1 equals 1. So, absolute 1 equals 1 and negative 1 raised to 2 equals 1. Therefore, the order of negative 1 is 2. Since 1/2 is an element of Q star and 1 is the identity, then 1/2 raised to n is not equal to 1. For any number of times n, therefore integer n does not exist such that 1/2 raised to n equals to 1 except 0. Hence, the order of 1/2 is infinite in the multiplicative group of non-zero rational numbers. Therefore, in Q star X, the absolute 1 equals 1 and absolute negative 1 equals 2, and every element has infinite order. Now, we are going to the next page, the exercise number 4. Prove that in any group, an element and its inverse have the same order. If absolute A is equals to n, A raised to n equals E. So, A raised to negative 1 times raised to n equals A raised to n times raised to negative 1 equals E raised to negative 1 equals E. Therefore, absolute A raised to negative 1 is equal or less than to n equals absolute A by the definition of order by the same reason. Absolute A equals absolute A raised to 1 times raised to 1 less than or equal to absolute A raised to 1. So we obtain absolute A equals absolute A raised to negative 1. Now, suppose that absolute A equals infinite. We need to show that absolute A is raised to 1 is equals to finite. As well, if not, absolute raised to 1 equals n for some n is greater than 0, then E equals A raised to 1 raised times raised to n equals A raised to n times negative 1, or equivalent to A raised to n equals E raised to negative 1 equals E. Therefore, absolute A is less than or equal to n and arise a contradiction. Hence, absolute A raised to negative 1 is equals to finite. Now we are going to next page, which is the exercise number 5. Without actually computing the orders, explain why the two elements in each of the following pairs of elements from Z sub 30 must have the same order 2, 28, and 8 to 22. Do the same for the following pairs of elements from U sub 15 is 2, 2, 8, and 7, 13. The groups Z sub 30 is closed under addition modulo 30, given that adding the two numbers generates the identity. Therefore, the number is additive inverse of itself, while u of 15 is closed under multiplication modulo 15, since we can determine the identity by multiplying the two elements, then they are the multiplicative inverse of one another. Hence, an element and its inverses have the same order. Now we are going to proceed to exercise number 6. In a group of Z sub 12, find absolute A, absolute B, and absolute A plus B for each case. For letter A equals 6, B equals 2, A equals 6, A plus A equals 12, equals 0. Absolute A is equals to 2. B equals 2, B plus B equals 3, 3 times B equals 6, 4 times B equals 8, 5 times B equals 10, 6 times B equals 12, equals 0. Absolute B is equals to 6. A plus B equals 8. 2 times A plus B equals 16, equals 4. 3 times A plus B equals 24, equals 0. So the absolute A plus B is equals to 3. For letter B, A equals 3, B equals 8, A equals 3, 3 times A equals 6, 3 times A equals 9, 4 times A equals 12, equals 0. Absolute A is equals to 4. B equals 8. So absolute B is equals to 3. A plus B equals 11 equals negative 1. So absolute A plus B is equals to absolute negative 1 equals absolute 1. So the answer is 12. For the letter C, A equals 5, B equals 4. A equals 5, 2 times A equals 10, 3 times A equals 15, 3 equals 3, 4 times A equals 8, 5 times A equals 1,313, equals 1, 6 times A equals 6, 7 times A equals 11, 8 times A equals 16, equals 4, 8 times 9 equals 9, 10 times A equals 14, equals 14, equals 2. 11 times A equals 7, 2 times A equals 12, equals 0. Therefore, the absolute A is equals to 12. B equals 4, 2 times B equals 8, 3 times B equals 12, equals 0. So, absolute B is equals to 3. A plus B equals 9, equals negative 3. So, the absolute A plus B equals absolute negative 3 equals absolute 3 equals 4. Now, we are going to the next page. Exercise number 7. Identify another generator of integers which generates all element integers under addition. In integers, generated 1 equals integers, each entry in the list, so on and so forth. Negative 2 times 1, negative 1 times 1, 0 times 1, 1 times 1, 2 times 1, so on and so forth, represents a distinct group of elements. Now let's proceed to another page, which is the exercise number 8. Make a Cayley table of a rectangle. Take a look at the Cayley table of the clean 4 group. What have you noticed? So, by making a Cayley table, we came up with this answer. By definition, the Klein 4 group is an abelian group with 4 elements, in which each element is self-inverse and it's which composing any two of 3 non-identity elements produces the third one. Therefore, the rectangle dihedral group is a Klein 4 group. Now, let's proceed to another page, which is the exercise number 9. Theorem C times A equals a subgroup. For each A in a group G, the centralizer of A is a subgroup of G. Let G be a group of X in G be any element, then the centralizer of X, C of X, then xy equals yx equals xz equals zx, so x times yz equals xyz equals yxz equals yzx equals yz times x, so yz is in C of x. Furthermore, 1x equals x equals x1, so 1 is in C of x. Finally, let y in C of x, then xy equals yx implies that y raised to negative 1, xy equals x implies that y raised to negative 1, x equals x, y raised to negative 1 implies that y negative 1 is in C of x. Therefore, C of x is closed under multiplication and inversion, so it is a subgroup. Now, let's proceed to another page, which is the exercise number 10. Suppose that A is a group element and A raised to 6 equals element. What are the possibilities of absolute A? Provide reasons for your answers. If A raised to 6 equals element, then absolute A must be and most 6. So only 1, 2, 3, 4, 5, 6 are possibilities. Furthermore, is A sub 4 equals E, then A raised to 2 equals A raised to 2, E equals A raised to 2, A raised to 6 equals 8, A raised to 8 equals A raised to 4 times raised to 2 equals E raised to 2 equals E. So, absolute A 4 equals to 4 is impossible. Similarly, if A raised to 5 equals E, the A raised to 3 equals A raised to 3 times A raised to 6 times raised to 2 equals A raised to 15 equals A raised to 5 times A raised to 3 equals E raised to 3 equals E. So, absolute A is equals to 5 is impossible as well. Therefore, only 1, 2, 3, 6 are possible because they are the divisor of 6. Now, we are going to proceed to exercise number 11. Show that if A is an element of a group G, then absolute A is less than or equal to absolute G. A element of G, absolute A, less than or equal to absolute G. Case 1, absolute A is infinite. A, E, A raised to 2, so on and so forth, A raised to N, all are distinct. A raised to I equals A raised to J is equivalent to A raised to I minus J equals E. Absolute A is less than or equal to I minus J. Absolute G is equal to finite. Case number 2, absolute A equals N, E, A raised to 2, so on and so forth, A raised to N negative 1 are all distinct. Absolute G is less than or equal to N. Absolute A is equals to N less than or equal to absolute G. Now we are going to proceed to another page, exercise number 12. Show that U of 14 equals generated 3 equals generated 5. Hence, U of 14 is cyclic, is U of 4 is equals to generated 11. We have U of 14 equals to the element of 1, 3, 5, 9, 11, and 13. We take powers of 3 to get 3 raised to 1 equals 3 raised equals 3 3 raised to 2 equals 9, 3 raised to 3 equals 27, equals 13, 3 raised to 4 equals 13, times 3 equals 39, equals 12, 3 raised to 5 equals 33, equals 5, 3 raised to 6 equals 1. This is all of U of 14. Hence, 3 generates the group. In a similar fashion, we have that 5 raised to 1 equals 5, 5 raised to 2 equals 11, 5 raised to 3 equals 13, 5 raised to 4 equals 9, 5 raised to 5 equals 3, 5 raised to 6 equals 1. So, U equals to U of 14. Thus, both 3 and 5 generate the group. On the other hand, 11 raised to 1 is equals to 11, 11 raised to 2 is equals to 12, 11 raised equals 9, 11 raised to 3 equals to 99, equals 1 is not equal to U of 14. So, 11 does not generate. Now, let's proceed to exercise number 13. Show that U of 20 is not equals to K for any K in U of 20. Hence, U of 20 is not cyclic. A group G is said to be cyclic if it can be represented in the form generated A equals A raised to N times A element of integers. Here, the element A is called the generator of the group. The element of the group U sub 20 are as follow. U sub 20 has the element of 3, 7, 9, 11, 13, 17, and 19. Therefore, with the elements, it can be seen that the order must be 8 of this group. Now, the order of element 1 is a group of 1. Similarly, for element 3. From the calculation, it can be seen that the order of the element is 4. Now, consider element 7. 7 raised to 1 congruent 7 of 20. 7 raised to 2 congruent 9 of 20. 7 raised to 3 is congruent to 3 of 20. 7 raised to 4 is congruent to 1 raised of 20. Again, it can be seen that the order of the element is 4. Consider the element 9. 9 raised to 1 is congruent to 9 of 20. 9 raised to 2 is congruent to 1 of 20. The required order of element 9 is 2. Consider the element 11. 11 raised to 1 is congruent to 11 of 20. 11 raised to 2 is congruent to 1 of 20. The required order of element 11 is 2. Consider the element 13. 13 raised to 1 is congruent to 13 of 20. 13 raised to 2 is congruent to 9 of 20. 13 raised to 3 is congruent to 7 of 20. 13 raised to 4 is congruent to 1 of 20. The required order of element 13 is 4. Consider the element 17. 17 raised to 1 is congruent to 17 of 20. 17 raised to 2 is congruent to 9 of 20. 17 raised to 3 is congruent to 3 of 20. 17 raised to 4 is congruent to 1 of 20. Consider the element 19. 19 raised to 1 is congruent to 19 of 20. 19 raised to 2 is congruent to 1 of 20. Therefore, the order of all the elements is not equal to 8. This showed that the group is not cyclic. And this is the end of my presentation. Thank you very much.